let me just review what we have done so far, and what we have done is the old quantum theory, in which we have calculated energy levels of quantum systems, and when I say quantum systems, I mean small microscopic systems. In particular, what I did was particle in a box. I also did harmonic oscillator, and I also did an atom. And what we have used here are something called the quantum conditions. That tell you that the action A, which is defined over a period P dq, I am just using dq for generalized coordinate, is NH, and that gave you the energies or energy differences. So this led to energies and energy differences between two levels. And once you know the energy difference between the two levels, so suppose two levels are m and n, let's say m is greater than n, then Em minus En over h gave you the frequency Mn. So we could calculate the frequencies of radiation. The other thing we did was to calculate to find intensities of these radiations. We have no recipe. No theory so far. The only thing that we have is, this is in contrast with, is the Maxwell's theory, where source of EM waves is well understood. The only thing that we have is Einstein's theory of A and B coefficients. So the only theory of matter radiation interaction in quantum theory is Einstein's theory of stimulated and spontaneous emission. In this theory, all we know is there exists a coefficient A, there exists a coefficient B. However, we do not know how to calculate it. So, although the theory developed so far gives a lot of information, and what all have we learned so far? It gives you atomic structure, it gives you periodic table, it explains spectrum, partially, because it gives you only the positions, right, and many other things. Still, the theory is not complete. However, the theory is far from complete. So, we do not really know how to calculate intensities, what is the structure inside, what is the quantum structure, and to understand all that, one had to make connections with other theories, particularly classical theory, which is well known, and that is where the correspondence principle came in. So, what we are going to discuss today is the correspondence principle that made a connection of what happens at quantum level and how quantum theory goes over to classical theory, and the way it helped. It's a really important principle, because the way it helped is that once we knew the classical results and how quantum theory should approach the classical result, one could sort of backtrack and extrapolate to the quantum regime what would happen there. So, it's a very important principle, and I am going to spend this lecture and the next lecture discussing this, and also see how one could look at the structure of classical theory and from that guess what should happen in quantum theory. So, to understand correspondence principle, let us start with an observation. And this observation is going to be, as the quantum numbers become large, the frequency of radiation emitted becomes the same as classical radiation frequency. And let me also remind you that the classical radiation frequency from an oscillating charge is the same as the frequency of periodic motion. Notice that I am using word periodic motion because oscillation does not mean a simple harmonic oscillation. It could be any periodic motion or its multiples. What I have written about classical result is known from classical theory. So, this is well known, and what the observation was that as quantum numbers become large, the frequency of radiation emitted due to quantum process, that is by jumping of an electron from one level to the other, becomes the same as the frequency in classical motion. Let us see that. So, I will take the example of particle in a box, and obviously we are going to assume it is a charged particle, because only charged particles radiate when accelerating. All right. So, that is besides the point, but particle in a box of length L has energy levels E, N is equal to h square n square divided by 2 m L square, that is the energy. Now, let us see what happens when this particle makes a jump from an upper level to a lower level. So, I am taking this particle in a box at an upper level n, lower level is n minus tau, where both are integers, and when this jump takes place, radiation comes out. And from Bohr's theory, I know that this frequency nu, when it is jumping from nth level to n minus tauth level, is going to be En minus E n minus tau divided by h, which is going to be h square over 8 ml square 1 over h n square minus n minus tau square. A correction. The energy is h square over 8 ml square times n square. So, the earlier slide I had written 2 ml square. So, let us proceed then, and therefore, nu n minus tau is equal to h square over 8 ml square 1 over h 2 n tau minus tau square. Right, this h cancels with one of the h's, and I get h over 8 ml square times 2 n tau minus tau square. Now, let us take the limit of n tending to infinity, that is n very large, and tau much less than n. So, transition, this implies transition from nth level to n minus 1, n minus 2 and so on, alright. And then I have nu n to n minus tau is equal to h over 8 ml square times 2 n tau, because I can neglect tau square, and this comes out to be, this 2 cancels, it gives you 4 h over 4 ml square times n times tau. Now, I am going to show that h n over 4 ml square is the frequency of periodic motion classically. So, the radiation which is coming out in the limit of n tending to infinity is equal to tau times nu classical. So, the radiation will have frequency nu classical or its higher harmonics. Let us now see that this is true. So, for this particle in a box where En is h square n square over 8 ml square is purely the kinetic energy, half mv square, and if I cancel this 2 with this, it gives me 4. So, therefore, I get v square is equal to h square n square over 4 m square l square, or v, the speed, equals h n over 2 ml. The time period for one complete motion is going to be when it goes to the right and comes back. This is 0 and L. Therefore, the distance for a time period is 2L. Speed is h n over 2 ml. Frequency nu is going to be 1 over t, which is nothing but v over 2L. Right, this gives me t equals 2L over v. So, this is v over 2L, which comes out to be h n over 4 m L square. This is the classical frequency. So, I can say that the classical frequency nu classical is h n over 4 ml square, and if you see it, what happened earlier. So, frequency emitted quantum mechanically is nothing but tau, where tau is an integer, nu classical. So it is as if when the quantum system is radiating in this large n limit, it is radiating either the classical frequency or its harmonics. We can understand this result, and I'll comment on it a little later through Fourier series. Let me give you another famous example, right? So hydrogen atom. For a hydrogen atom, the energy of the nth level is given as minus m z square e raised to 4 over 32 pi square epsilon 0 square h square n square. That is the energy of a hydrogen atom, and since I am taking Z, so let me call this hydrogen like atom with nuclear charge Ze. So when in a hydrogen atom the transition is taking place from n to n minus tau, then the energy radiated h nu comes out to be E n minus E n minus tau, which will be m, where m is the mass of the electron. Z square is going to be m z square e raised to 4 divided by 32 pi square epsilon 0 square h square times 1 over n minus tau square minus 1 over n square. And this comes out to be m z square e raised to 4 divided by 32 pi square epsilon 0 square h square. Inside I am going to get n square minus n minus tau square divided by n minus tau square n square. And let me now take limit n tending to infinity and tau much less than n, then you will see that h nu comes out to be m z square e raised to 4 divided by 32 pi square epsilon 0 square h square, and you get n times 2 tau divided by n raised to 4, which is nothing but, so h nu comes out to be m z square e raised to 4 divided by 32 pi square epsilon 0 square h square times 1 over n cube times 2 tau, which is m z square e raised to 4 over 32 pi square epsilon 0 square h square. 32 will cancel, so let me cancel this. This becomes 16. So let me write this as 16 pi square tau over n cubed. And I am claiming that this is again tau times nu classical times h, so that nu when it's making a transition from n to n minus tau is nothing but tau times nu classical. I'll leave it as an exercise for you to show that this is nu classical, and this is how you proceed. En is given to be minus m z square e raised to 4 over 32 pi square epsilon 0 square h square n square, and this is also equal to minus 1/2 mv square. From this you can find what this speed of the electron in the nth orbit is. So v n can be found. And once we have v n, you also know Bohr condition gives you m v r equals n h over 2 pi. So you can find this implies that R n can be found. and Vn by Rn divided by 2 pi gives you new classical. So that would come. So what we have learned through these two examples is that if there is a transition from nth level to n minus tauth level, tau is also an integer, then in the limit of large n, right, the new emitted is equal to a harmonic of new classical. So this is the observation. Is this observation a coincidence, or does it have something deeper? So let me raise this question. Is the observation these through only two systems a coincidence, or is it true in general? That is the question, and the answer is this is true in general. And this comes from the classical theory, which says, suppose there is a system, I have considered two systems here. I have considered the system of particle in a box. I have considered an atom in which the electron is moving around in a circle. I will also consider a system harmonic oscillator. And what I will show you is that in these systems, the frequency of oscillation is going to be partial E over partial A, where E is the energy and A is the action. Let me elaborate on that a bit. So I am claiming that I will show it only through examples. More general proof requires a little more understanding of classical mechanics, which at this time is slightly beyond this course. So I will do only through examples that if I take a system with energy E and action A, let me remind you what these are. So for example, if there is a particle moving around in a harmonic oscillator, action is given by P dx. In this particle in a box, again action will be given by integral P dx, and for this particle going around in a circle, the action, remember, was given by the angular momentum d phi, if you just recall from previous few lectures. And action therefore is a constant, is a number given for this orbit, and E, the energy for this orbit, can be written as a function of this action and some other parameters of the system. Obviously, you see that if I change the action value, I will change the orbit, and therefore the energy is also going to change. And what is claimed is that dE, dA for a particular orbit is going to be the frequency of that orbit, classical.